Welcome to week 3 of our course, Boltzmann Law, Physics to Computing. This is the first lecture for this week. Now, as you may recall, last week we had started by introducing this time sampling method. And so far we have had these two methods that we have been talking about, namely the general Boltzmann law operating in 2 to the n space and this time sampling method operating in n space. Now this week we'll introduce a third method, which also actually operates in 2 to the n space, but as you'll see, it gives us a lot of insight into this, how the sampling method works, and leads to this concept of Feynman paths, which is useful to connect to the world of quantum computing. Now, let's get started just talking about this transition matrix method. What is it? Well, the idea is that if you have a system in some configuration I, denoted by say 111,001, that's a configuration, and you want to know what will happen at the next time step. And the answer is that in a probabilistic circuit, it will go to different configurations J with different probabilities. And those are the probabilities that should appear in the ith column. So the ith column, the column tells you what's the input, that is what the configuration was at time t. And the jth row then tells you the probability that the system will go from I on to j. Okay? And in general, you can take the probability distribution function at a time t, multiply it by w, and it will give you the new probability distribution at time t plus 1. So this matrix kind of propagates your probability distribution function from one time point to the next. And one very important property of this matrix, these matrices, by the way, are called stochastic matrices, and one important property is that every column must add up to 1. Why is that? Well, because this column represents the probability that the system will go to some state j, given that it is in I at this time. Well, of course, it must go somewhere, which means if I add up all the j's, the answer should be 1. As I mentioned, this matrix appears in many diverse fields, the same matrix, but here, of course, we are describing a particular problem using this W matrix. Now, one important property, what makes it so useful is there are several properties here. Now, one important property is that it has an eigenvalue equal to 1. So, of course, this is a huge matrix. So, say 2 to the power n by 2 to the power n. So, it has 2 to the power n eigenvalues. But one of these, actually the largest one, the one with the highest magnitude, is equal to 1. Now, how do I show that? Okay, so to show that, consider the transpose of the W matrix. So for the W matrix, the columns add up to 1. So for the transpose, it is the row that adds up to 1, right? So W transpose Ij summed over J is 1. Now, what that means is that if you consider this constant vector, which is a relatively trivial vector, one where all its components are equal to a particular number, C. What you can show is that a constant vector is actually an eigenvector of this transpose matrix W. How do I show that? Well, consider the ith element of Wt times C. Well, in matrix notation then, that amounts to like summation over j Wt ij times Cj. This is just the rule for matrix multiplication, and what it gives you is the ith element of the product. Well, but Wt has this property, right, of stochastic matrices, that Wt summed over j ij is equal to 1. So this quantity is just 1. And Cj, that's the jth component of C, well, that's just this constant. So finally the point is, when I multiply this, I get the ith component is just this constant. So basically, I'm just getting back this same column vector. And so Wt times C is equal to C. In other words, this constant vector C is an eigenvector of W transpose and has an eigenvalue of 1. Now, I am of course interested not in W transpose but in W. And then there is this theorem that you may remember from somewhere in linear algebra, that W and W transpose have the same eigenvalues, but not necessarily though the same eigenvectors. The eigenvectors could be same but don't have to be. But the point is they will always have the same eigenvalues. And so what we can assume then, we can deduce, is that since W transpose has eigenvalue 1 and eigenvector C, W must also have an eigenvector, but not necessarily C, we'll call it P, but the eigenvalue is 1. So W times P is equal to P. Now, this P is what you could call a stationary distribution. Why is that? Well, you see the W matrix, as we discussed, it takes the probability distribution function from one point in time and propagates it to the next point. Now, because of this property, what it means is that if at a given time t that you have a distribution p, then W times P is equal to P. So at t plus 1 also you'll have the same distribution. So in other words, the distribution, once it reaches P, it will stay that way forever. And so you call it a stationary distribution. Now what if initially at time t, the distribution was something else? I'll call that Q. It's not equal to P, something else. Well, the answer is that after a few time steps, and we'll talk about how many, the probability distribution function will converge to P. So we started out with something different, but what will happen is it will become P. Why is that? Well, to show it, one way to think is take the Q and write it in terms of the eigenvectors of the W matrix. So as I said, P is one of the eigenvectors with eigenvalue 1. Let's say there's another eigenvector A with eigenvalue lambda. And of course, there'll be many more eigenvectors. And some eigenvalues will even be complex. But here, just for illustrative purposes, I'm considering one other. The argument we'll make will apply to all of these other eigenvectors. Now, you see, if at time t we have P plus A, then what will happen at time t plus 1? Well, it will get multiplied by W, and W times P will give me P, but W times A will give me lambda A. Why? Because A is also an eigenvector of W, but with an eigenvalue lambda. And so every time I propagate one time step, the P stays P, but the lambda A, that part keeps picking up a factor of lambda. So after n time steps, I have P plus lambda to the power n A. And the point is, I mentioned before, that this eigenvalue of 1 is actually the one with the largest magnitude. Every other one, all other lambdas, they may be complex, but the point is their magnitude will be less than 1. That's one of the properties of this stochastic matrix. And so because it's less than 1, when you raise it to the power n, it gradually disappears. If you take 0.1 and raise it to the power 100, it becomes a very small number. Okay? And so eventually only the P remains, everything else disappears. Well, how many time steps does it take for these other components to disappear? Well, you can estimate it this way, that take a lambda and to the power n, and you can write it mathematically in this form. You see, you can always write lambda as e to the power log lambda, natural log of lambda. That's an identity. So you could take this quantity and write it this way. What that means is that if the number of time steps n is equal to minus 1 over log lambda, then you see this lambda to the power n would be e to the power minus 1, which means after this many time steps, this component will have decayed to 1 over e of its original value. And so how much is that? Well, if lambda were, say, a little less than 1, write it as 1 minus epsilon, then you can show that this number will be 1 over epsilon. This is an approximate result, but it works well if epsilon is small. So what that means is, if, say, this eigenvalue happened to be 0.99, that means epsilon is 0.01. Then it would take like 100 time steps before this component becomes 1 over e of its original value. So bottom line is, we have this W matrix, the transition matrix. You can use it to generate a chain of time samples, and they will tend to this distribution P, the stationary distribution P. And what distribution is it? Well, it's given by the eigenvector of W with this eigenvalue 1. Now, what we want is, of course, a method of time sampling that gives me where the samples obey this correct Boltzmann law, because Boltzmann law is what I'm generally using as my standard, and this whole time sampling method, or however you're doing this, you want to get that Boltzmann distribution. Otherwise, this method wouldn't be much use to me. You see, if it was generating some other distribution. Now, how do we make it match? So how can you make this stationary distribution match it? And one way is to impose detailed balance, which means if we require that this Pi times Wji, which means the probability the system has a configuration I times the probability that it will then go to j, should be equal to the reverse, that is Wij times Pj. And I can show why that works, because if this is true, then I can show that W times P would be equal to P. How do I show it? Well, what's W times P? Well, if you want the jth component, you would say Wji Pi sum over I. That's the rule of matrix multiplication. And that then should give me, that's the jth component of the left-hand side, should be equal to the jth component of the right-hand side, which is Pj. So question is this equal to this? And the way you can show it's equal is by using this detailed balance rule. Instead of Wji Pi, we write Wij Pj. And then we make use of the fact that W is this matrix where if you sum over this first index, that means which is like summing these columns, the answer is 1. So this part of it then just becomes 1, and we are left with Pj. So basically what we have shown then is that as long as this detailed balance is obeyed, Wp will be equal to P. What that means is this Boltzmann distribution then will be the correct stationary distribution of W. So, by imposing, so when I write down W then, when I write down the stochastic matrix, what I need to make sure is that this condition is satisfied, Pi over Pj. And what is Pi over Pj? Well, that's this exponential of minus Ei minus Ej. And note how this constant disappears. You see, when I take the ratio. If you had asked me what is Pi, I would have to go and calculate this constant to make sure everything adds up properly to 1. But if you just ask me the ratio, that I can write down if I know the energy function. And this is something that is very useful when doing these sampling techniques. There's a very well-known algorithm that is widely used in statistical physics. It's called this Metropolis algorithm. And there, the way you choose your W's, these transition matrices, is to say, okay, consider any two states, I and J, and let's say I has a bigger energy than J. And I'm currently sitting at I, and I'm trying to figure out what is the probability, how do I probability of going to J. And the answer is, again, to satisfy detailed balance, this ratio must be equal to this exponential. So the way I choose it is the probability for going down in energy, which means for I to j, from the higher energy to the lower energy, that is 1. That's the W, that's 1. Whereas the Wj to I, that's the part where you choose it proportional to this exponential of minus Ei minus Ej. So this is the ratio in which you'd choose those probabilities. Okay. Now, and what makes this, I guess, practically useful is the fact that I didn't have to know z, this constant in front, in order to employ this method. Okay, so that kind of is what we wanted to talk about in this lecture, where I wanted to introduce this transition matrix, which is a stochastic matrix with some very interesting properties, and whose stationary distribution gives us this probability that we want, and the way we can ensure that we get the correct Boltzmann distribution is by requiring this detailed balance. And at the end I mentioned this Metropolis algorithm that is often used, but what we have been using in this course and what we'll be talking about more is a different sampling method, and that's this Gibbs sampling, and that's what we'll pick up in the next lecture. Thank you.